I've talked about how a rotating coil in a magnetic field can induce a voltage, an alternating voltage that keeps changing direction. And in fact, this is how our electric power is usually generated in electric power station. And when it's transmitted to our house with very long power cables, this is also the voltage that we receive from our mains socket. So let's look at this alternating voltage or alternating current, as it is often called, in a bit more detail. So suppose that I have a voltage that is described by this formula: V0 sine omega. Try again. V0 sine omega t. And I know that if I sketch a graph of that, it would just look like a sine curve. Against time and voltage. And suppose that I connect it to a light bulb. So let's see. Now instead of drawing a battery, we think of battery as something that provides a direct current, or DC, that is constant and does not change direction. So for an alternating current, or an AC, as is often called in short, AC for alternating current, let's write that down, alternating current. Okay, so instead of using the two lines in a circuit to represent a battery, we often draw a squiggle or a little sine wave in between two dots, dot here and a dot here, and then we use this instead of the symbol for battery. And I want to draw a circuit that shows that it's connected to a light bulb. Okay, so this is my light bulb. I'll think of this as a filament lamp. So there is a filament inside with high resistance, so that when a current goes through this light bulb, the filament gets hot and it lights up. Okay. Now, I shall assume that in this case, we're not actually using the mains directly, which is maybe a few hundred volts. In this example, I'm just going to think of this voltage as, say, just let's say it's 1.5 volts as well, just like a battery. And suppose that the resistance is 10 ohms. Okay, and because of this alternating voltage, we will have a current flowing through the circuit. Now, this current would not just go in one direction, it will keep changing direction, because the voltage keeps changing direction. So that's why it's called an alternating current, in the sense that it keeps changing direction. Okay. Now we know how to use Ohm's law in a simple circuit with a simple battery. Now, Ohm's law is V equals to IR. So if this is just a battery of 1.5 volts, we know how to use Ohm's law to find the current. But in this case, it's an alternating current. So can we still use Ohm's law? In fact, we can. It just means that both the voltage and the current will keep changing. The resistance is still fixed. In this case, 10 ohms. Okay, so what is the current? Is there an answer, or is there a formula for the current? There is. If I rearrange this to find the current, I can divide both sides by R to get I equals to V over R, and then I can find the current by substituting the formula for the voltage. So if I do that, V is V naught sine omega t over R. Okay, so in this case, we can find V over R actually. V over R, let me try that. V over R, if I calculate this, is actually 1.5 divided by 10. So that's 1.5 divided by 10. That would be 0.15 ampere. Now I'm going to call this I naught. So this means that the current I can write the current I as I naught times sine omega t. Write it down here. So the current I can be written as I naught times sine omega t in the same form as the formula for the voltage. So if I now sketch a graph of the current, it will look pretty much the same as for the voltage, because both the current and the voltage follow the sine curve. So it looks like this. Against time. And for the voltage, the maximum value is 1.5 volts. Units of volts, time in seconds. Current is in amperes, and the maximum current is I naught, which is 0.15 ampere in this case. Okay, and this is V naught, and this is I naught. Now the graph here is a sine curve, and it looks just like what we have seen. It looks just like the kind of graphs we have seen for the displacement time graph in simple harmonic motion, and even for waves. So there are certain descriptions about such a wave-like graph that we can actually take over from what we know about simple harmonic motion and waves. For example, there is the name for this maximum amount, voltage or current, is called the amplitude. Okay, so for example, that would be the amplitude of the current, and that would be V0 would be the amplitude of the voltage. What about the time for one cycle? the time, I call that T. Here I call that T. Now the time for one cycle is called the period, just like we called it for the simple harmonic motion case. Okay, and we would really like to relate it to the omega here. The omega here is the angular frequency, or in circular motion is called the angular velocity. In simple harmonic motion and in waves, we call it the angular frequency. Now, let's look at this a little bit more. We think of, in circular motion, we think of the angular velocity, which corresponds to the angular frequency here. We think of it as the angle over time, right? The angular displacement over time. In this case, in one period, the angular displacement would be 360 degrees, or 2 pi radians. Right? We prefer to do this in units of radians rather than degrees. And this for simple harmonic motion and for waves. Okay, so that's the angular frequency. Now, but we also know that the frequency, as in the number of cycles per second, is related to the period by 1 over t, because there is exactly one cycle in one period. So we have seen all these relations before. Now, let's take a look at a typical example to see what the numbers look like. For example, the mains power supply that we get in a house would typically have a frequency of 50 Hertz or so. Okay, so the current and voltage will be changing direction 50 times a second. So let's take a look at what the period would be when the frequency is 50 Hertz. The period would be, from this relation, just 1 over the frequency. And if the frequency is 50, this is 1 over 50. And 1 over 50 is 0.02 of a second. So that would be the period of the AC that we get from the mains in our house. Okay, so there is amplitude, there is period, there's frequency, there's angular frequency. Okay, that might do for now.